Hey everyone, welcome, I am Amjith, and today I am gonna share with you control valves. The control action in any control loop system is executed by the final control element. The most common type of final control element used in chemical and other process control is the control valve. A control valve is normally driven by a diaphragm-type pneumatic actuator that throttles the flow of the manipulating variable for obtaining the desired control action. A control valve essentially consists of a plug and a stem. The stem can be raised or lowered by air pressure, and the plug changes the effective area of an orifice in the flow path. When the air pressure increases, the downward force of the diaphragm moves the stem downward against the spring. Classification of control valves. Control valves are available in different types and shapes. They can be classified in different ways based on action, number of plugs, flow characteristics. Classification of control valves based on action. Air to open. If the air supply fails, the control valve will be fully closed. Air to close. If the air supply fails, the control valve will be fully open. Control valves operated through pneumatic actuators can be either air to open or air to close. They are designed such that if the air supply fails, the control valve will be either fully open or fully closed, depending upon the safety requirement of the process. For example, if the valve is used to control steam or fuel flow, the valve should be shut off completely in case of air failure. On the other hand, if the valve is handling cooling water to a reactor, the flow should be maximum in case of emergency. The schematic arrangements of these two actions are shown in figure below. Valve are air to close type, indicating, if the air fails, the valve will be fully open. Opposite is the case for valve B. Classification of control valves based on number of plugs. Control valves can also be characterized in terms of the number of plugs present, as single-seated valve and double-seated valve. The difference in construction between a single-seated and double-seated valve are illustrated in Fig. Here. Only one plug is present in the control valve, so it is single-seated valve. The advantage of this type of valve is that it can be fully closed and flow variation from 0 to 100% can be achieved. But looking at its construction, due to the pressure drop across the orifice, a large upward force is present in the orifice area, and as a result, the force required to move the valve against this upward thrust is also large. Thus this type of valves is more suitable for small flow rates. On the other hand, there are two plugs in a double-seated valve. Flow moves upward in one orifice area, and downward in the other orifice. The resultant upward or downward thrust is almost zero. As a result, the force required to move a double-seated valve is comparatively much less. But the double-seated valve suffers from one disadvantage. The flow cannot be shut off completely, because of the differential temperature expansion of the stem and the valve seat. If one plug is tightly closed, there is usually a small gap between the other plug and its seat. Thus, single-seated valves are recommended for when the valves are required to be shut off completely. But there are many processes where the valve used is not expected to operate near shut-off position. For this condition, double-seated valves are recommended. Classification of control valves based on flow characteristics. Flow characteristics describes how the flow rate changes with the movement or lift of the stem. The shape of the plug primarily decides the flow characteristics. The flow characteristic of a valve is normally defined in terms of inherent characteristics and effective characteristics. An inherent characteristic is the ideal flow characteristics of a control valve and is decided by the shape and size of the plug. When the valve is connected to a pipeline, its overall performance is decided by its effective characteristic. Based on inherent, ideal characteristics, control valves are classified into three, such as quick opening, linear and equal percentage. The shape of the plug decides how the flow rate changes with the stem movement, or lift when the pressure drop across the valve is assumed to be held constant. This classification is basically done on relationship between the valve stem position and the flow rate through the valve. As the stem and plug move with respect to the seat orifice, the shape of the plug determines the amount of actual opening of the valve. Quick opening type. This type of valve is used predominantly for full-on, for low FF control applications. The valve characteristics shows that a relatively small motion of the valve stem results in maximum possible flow rate through the valve. Such a valve, for example, may allow 90% of maximum flow rate with only a 30% travel of the stem. Linear type. This type of valve has a flow rate that varies linearly with the stem position. It represents the ideal situation where the valve alone determines the pressure drop. Equal percentage type. A very important type of valve employed in flow control has a characteristic such that a given percentage change in stem position produces an equivalent change in flow, that is, an equal percentage. Generally, this type of valve does not shut off the flow completely in its limit of stem travel. Thus, Kmin represents the minimum flow when the stem is at one limit of its travel. At the other extreme, the valve allows a flow makes as its maximum open valve flow rate. Directional control valves. In directional control valves, it is basically the directions of the flows that are controlled and not the magnitudes. Directional valves can be characterized depending on the number of ports, the number of directions of flow that can be established, number of positions of the valve, etc. They are mainly classified in terms of the number of flow directions, such as one-way, two-way or four-way valves. Directional valves are often operated in selected modes using hydraulic pressure from remote locations. Such mechanisms are known as pilots. Thus a valve that may be blocking the flow in a certain direction in absence of pilot pressure, may be allowing flow, when pilot pressure is applied. Check valve. In its simplest form, a check valve is a one-way directional valve. It permits free flow in one direction and blocks flow in the other. It is analogous to the electronic diode. Symbol of check valve is shown below. The direction of the arrow shows the direction for free flow. In its simplest form of construction, a check valve is realized as an inline ball and spring. Pressure from the left moves the ball from its seat so to permit unobstructed flow. Pressure from right pushes the ball tight onto the seat, and flow is blocked. In some valves a poppet is used in place of the ball. In some other construction, the valve inlet and outlet ports are made at right angles. Pilot-operated check valves. Pilot-operated check valves are designed to permit free flow in one direction and to block return flow, unless pilot pressure is applied. However, under pilot pressure, flow is permitted in both directions. They are used in hydraulic presses as pre-fill valves, to permit the main ram to fill by gravity during the fast approach part of the stroke. They also are used to support vertical pistons which otherwise might drift downward due to leakage past the directional valve spool. With no pilot pressure, the valve functions as a normal check valve. Flow to bottom is permitted but the reverse is blocked. If pilot pressure is applied, the valve is open at all times, and flow is allowed freely in both directions. The check valve poppet has the pilot piston attached to the poppet stem. A light spring holds the poppet seated in a no-flow condition by pushing against the pilot piston. A separate drain port is provided to prevent oil from creating a pressure buildup on the underside of the piston. Reverse flow can occur only when a pressure that can overcome the pressure in the outlet chamber is applied. Possible application of the valve can be to permit free flow to the accumulator, while blocking flow out of it. If the pilot is actuated, the accumulator can discharge if the pressure at the inlet port is lower than the accumulator pressure. Relief valves. Relief valves are used for regulation of pressure in hydraulic systems for protection of equipment and personnel. The spring keeps the valve shut until a pressure set by an adjustable spring tension is reached, which pushes the spring up to relieve the pressure by connecting the inlet to the drain.